Happy to present a topic of quantum machine learning at the optimization conference. My name is Alexey Melnikov. I'm working for Terra Quantum. During the last, I would say, around 13 years, I'm working on the topics of quantum computing and machine learning. Of course, it also touches very well the topic of optimization. And in Terra Quantum, what we do with quantum machine learning, we develop algorithms for solving industrial tasks. And that's what I will talk about today. How, from a theory of quantum machine learning, achieve some practical solutions with quantum machine learning. So here is the outline of my presentation. I plan to talk briefly about the definitions of quantum machine learning and give you some introduction. Then I will talk about quantum enhanced machine learning and our expectations, give intro to quantum neural networks, how to theoretically analyze those objects, talk about hybrid quantum classical neural networks, so this combination of classical and quantum ML, and proceed to the applications, use cases, and the engineering this solution for industry. So to start, the field in principle of quantum machine learning is defined broadly. So what you can see in literature is any combination of the words quantum and ML would classify some quantum machine learning field. This is the field where we consider data and machine learning algorithms. Data is something that is being loaded to a machine learning algorithm for processing. And it's defined broadly, so it could be that something in this picture is being quantum. If we look at the number of publications that you look on, for instance, arXiv, as we did with our script, to check how many papers could be classified as related to quantum machine learning that mention, some combination of quantum and classical as in the paper, or but machine learning and quantum must be present in this paper. We see there's a really growing number of papers that can be in principle related to the field to some extent. As I said, something in the picture has to be quantum, so it can be data that is being quantum or the algorithm being quantum. So what we define as quantum data, this is information from quantum measurements, information coming from quantum systems, and classical data is all other data. As for the machine learning algorithm, we define a quantum machine learning algorithm as a set of instructions that can be performed on a quantum computer. So it must be an algorithm which is a sequence of some quantum operations, some sequence of pulses, sequence of quantum gates, whereas classical machine learning algorithm is the rest. So the set of algorithms that doesn't fit this definition of quantum ML algorithm. And this is very important for our discussion to clarify this definition, because what we can see in principle, even though we will consider quantum machine learning algorithms, sometimes you can think of running this quantum machine learning algorithm on a classical computer. It could be also a viable solution. This gives us a standard combination of opportunities to consider if our data is classical or quantum, algorithm classical quantum. We can see 4 different combinations. For instance, if we look at classical, this might be the most boring part, but it's also the field where so-called quantum physics inspired machine learning algorithms are being born. For instance, tensor network techniques in machine learning, they're purely in the classical algorithmic space for classical data. However, they are inspired by physics, especially quantum physics. The same we can say about algorithms like Boltzmann machine or projective simulation in reinforcement learning. These are all quantum physics inspired, although classical. Another approach would look at classical algorithms for quantum data. That would be, for instance, correcting errors in a quantum computer. We use classical reinforcement learning technique to do quantum error correction, or detecting phase transitions from data, or designing new quantum experiments and protocols. Another field which is very exciting is a fully quantum machine learning approach, where we learn unknown quantum states on processes with quantum algorithms. We detect phases with, for instance, quantum convolutional neural networks, or we first map a classical task, classical environment to a quantum system, and then do a quantum reinforcement learning with a quantum environment. This would be a quantum setting. What I will consider in my talk is quantum enhanced machine learning, where our data is classical and algorithm is quantum. Examples of those are algorithms of quantum support vector machines, quantum neural networks, quantum Boltzmann machines, quantum principal component analysis, quantum k-means, many others. In this field, we need to first define what are we interested in to find out. So because of this, I would like to talk about our expectations from quantum enhanced machine learning. So here's a bit of a technical slide with which I want to tell that we look primarily at two components of the performance of an algorithm. One is speed, another is accuracy. So you can imagine it that we would try to enhance the speed of training or speed of inference of a quantum enhanced machine learning algorithm. With accuracy, we would like to achieve better solution quality, so low loss function, high accuracy. Ideally, we would like to improve on both with quantum computing. To do this, for instance, when we look at speed, we in principle want to be as accurate as classical, but do it faster. Usually that would mean to require less iterations to solve the task. If classical ML would need 100 epochs and quantum can do it in 50, that would be a success for us. To achieve this, we usually look at quantum analogs of a classical model in case there's a neural network solution, in case there's a k-means solution or Boltzmann machine. We look at this classical model and try to quantize it and find that quantum model can give accuracy similar to classical, but has expectation of a speed advantage when being executed on a quantum computer. And this relies on a quantum hardware speed up. We cannot achieve this speed enhancement without a quantum computer, because if we would run such a quantum algorithm on a classical computer, that would definitely not serve the purpose, and it's having a quantum analog of a classical model which runs on a classical, let's say, HPC, would not give us a speed advantage. So this is very, very much hardware tied setting. We see that hardware requirements for quantum machine learning practical tasks is some distant future, requires some advancements in quantum computing hardware. With algorithms, the challenge here is that there are dequantization techniques that provide us efficient quantum-inspired classical techniques, and they outperform quantum algorithms. And the proofs where we get advantage in speed, they are almost always, what we see on data sets that are not practically relevant. So there are many challenges of this speed enhancement field direction. If we look at the accuracy, we're in the following setting. We want to be, in principle, as fast as classical, but we want to be accurate in our predictions, more accurate. Usually that means for us to fix the time resources and don't talk about scaling, we just fix it for a given problem. Don't talk about exponential scaling or potential exponential quantum advantage. And we find, again, a quantum analog of a classical model and demonstrate that quantum model accuracy is better than classical in a given problem. And this approach of searching for better accuracy relies more on quantum algorithmic logic rather than relying on quantum hardware speedups. Because in principle, a quantum algorithm might be just more efficient in processing data in comparison to the classical analog. And I will talk more about this related to quantum neural networks. The challenges here are the following. The same we cannot use really quantum hardware for industrial data sets, but on the other hand we can do classical simulations of those for small quantum systems. Algorithms don't have a provable advantage in any broad practical problem class, and that means advantage is strictly problem dependent. An example of this is on this slide. If you look at the middle, we, for instance, see a comparison of quantum versus classical. On the x-axis, we see the number of epochs we use to train, so number of iterations of our algorithm, and on the y-axis, the loss function, the quality of the solution inversed. And we see that quantum has a lower loss, meaning it outperforms the classical. In this particular setting, I'm not talking in detail about. This doesn't give us any conclusion about, scaling, about quantum advantage in general sense, but on this particular problem, in this particular setting, it turned out that quantum just outperformed classical. And that's what we are looking for, more and more examples of such settings, and try to systematically understand what's happening, what's the reason for this improvement, and how to scale it to more problems. To talk also to mention, of course, if the quantum system is small, it's actually much more efficient to run it on a classical hardware rather than quantum hardware. And this gives us interesting setup where we can also think of types of hardware that we're using to run our quantum algorithms. Could be quantum or classical. And we again end up in this 4 situation scenario where we can have quantum algorithm running on classical hardware or quantum hardware. And in principle, the same for classical algorithms. Now let me be more specific about quantum algorithms and talk about quantum neural networks. By quantum neural network, we can define several concepts, but I will define it as following. This is a quantum circuit which has layers of operations, and these layers have 4 different types. One type is encoding type, where we can use quantum gates parametrized by input data. In my notations, for instance, that means we do, in the first encoding block, we do Y rotations, single qubit Y rotations, and the angle of this rotation is the input real number x1, x2 up to xn for n qubits. And there is a trainable operation, so it's a parametrized operation with rotation angles, but these rotation angles are modified by optimization techniques. There's a trainable encoding. It's a mix of encoding and trainable operations where you see the rotation angle is parameterized by both input data and the weights that have been modified by optimization algorithm. And there's the fourth type of a layer. It's a readout layer where we can choose how we measure qubits and get data out of a quantum circuit. So if our quantum circuit is defined in this parametrized way with layers depicted here, I would call it a quantum neural network capable quantum circuit. In simple way, the way we think of it is that there is a classical analog, a vanilla classical neural network or multi-layered perceptron, where input data enters neurons, and then there are weights that are being trained, modified by an optimization algorithm that compute the values of neurons at the next layer. For this 3 to 4 neural network layer, we can compute the output, and it's defined by this y1, y2, y3, y4, and a rectified linear unit nonlinear activation function, which gives a maximum between 0 and y1. We can then analytically write down what's the output function, which is a function of inputs x and weights w, and you can see the formula. The same we can do for a quantum system, in which we have an evolution of a quantum state, psi wx, and the measurement m, and write down what's the output function depending on x and y, and w. You can immediately see these are different mathematical functions, although they both capable of transforming 3 inputs to, in principle, 3 outputs. And now the question is, where do we think the left-hand side function could be more beneficial than the right-hand side function? That's, I think, the basic question. To demonstrate how all these functions really relate to machine learning, I can give you a small examples. For instance, let's take a simple single qubit quantum neural network. The first picture demonstrates how it works for a quantum neural network with just one gate and one measurement. We can do a rotation around the y-axis, and angle is our input data x. If we compute the function from the formula from the previous slide and do the z measurement, we get the following analytical expression, and we can plot it depending on the x. Let's say x is from 0 to 13. We get a simple harmonic function here. First, we notice that it's, of course, one thing is that it's periodic, and it makes sense to rescale our input data to get rid of this periodicity in the expectation value. And that's what we usually do. We rescale input data from 0 to pi over 2. This is not an interesting function by itself, because in order for it to become a good machine learning model, all your data have to be, let's say, on a cosine function. Let's see what happens if we add the second gate. If we add the second gate and now we parameterize it with parameter w, something we can tune with optimization techniques. For instance, we measure, we see what's the outcome. Does the outcome matches our training data. If it doesn't match, we modify W. And we see we already with this additional gate are able to change the amplitude of our function. Not much, but already one single gate allows us something. If we keep adding, so I added one more gate that encodes the same data point X, and then one more gate that is parameterized. And with this, we already can observe that we can not only change the amplitude, but we can also change frequencies. And in general case, doing more gates, going deeper, enhances the expressivity of a quantum circuit. That means we can do more complex functions by going into deeper circuits. So, and moreover, repeatedly encoding data through parameterized gates enables us richer functional representations. So it's important not only to add parameterized gates that are tunable, but also the gates that re-upload the data. This is exactly the same circuit, but just with W1 and W2, the weights that are being equal. On the previous picture, what you saw, we made W1 plus W2 equal to pi over 2, just to make some limitations for what W's can we take. In case we lift the restriction of which values W1 and W can take, that would be a bit of a messy plot, but you will be able to see that amplitudes and frequencies can be tweaked much, quite well, even with this very simple single qubit example. In case we go to more dimensions, so we go to not more dimension, but further deeper circuits. So for instance, do not 2 repetitions, but n repetitions. What was actually found out that the number of coefficients, the number of, let's say, the complexity grows exponentially, and the complexity is defined by the mathematical functions that are being generated by a quantum circuit. And it's very good to think of a quantum circuit as a truncated Fourier series, because all gates, are rotations, and we can decompose the expectation values into the functions that are functions of the input X and W's. And this truncated Fourier series has k terms, and k, the number k, grows exponentially with number of repetitions of encoding and trainable layers, which is quite a powerful concept for quantum networks. So can go up to exponential. Of course, we can choose settings where it grows linearly. Differently. So this is something for, let's say, quantum engineers to figure out for which data sets, which architecture would work best. We can also trade depth for width of a circuit, so we don't have to, let's say, work in a single qubit, say, which very deep. It would has many limitations in the way we can train such a circuit. So actually going to more qubits and the circuit being shallower has a lot of benefits in mathematical terms. Here are some demonstrations why going kind of into the setting of more qubits introduces an advantage, because we can tune more coefficients in a truncated Fourier series. I would skip this, and this just demonstration that each component in a truncated Fourier series, although even if it's accessible, it doesn't mean that we can easily modify the amplitude of this component well. And depending on the architecture chosen, different architectures would show different flexibility in how they can modify these components. This boils down then to how do we engineer quantum neural networks, which architectures are being better. Here are a couple of examples. The first one that I will use a lot is a quantum depth infused neural network layer, where we first load some data, a portion of data, then we do so variational operation is a trainable operation. We first do some training module, then we do embedding, where we load some portion of the data. We again do training with variational, and then we repeat, but with new chunk of data. So we keep encoding new data in the width, in the depth of a circuit, and by this we are capable to, in general, encoding and processing well up to exponential number of input data in circuit in number of qubits. Another layer could be to cut entanglement links between some of the qubits to not allow, let's say, connection between all chunks of data. This would lead to parallel quantum layers, but there are many more. So the question is how to analyze which one is good, which one is not. One way is to look at this truncated Fourier series for at least small number of qubits, where we can do it analytically, and then simulate for given data that we have in our machine learning data set to see how well we can tune the amplitudes in the truncated Fourier series terms. For instance, the picture on the right shows us this violin plot where we have imaginary real component of an amplitude in the truncated Fourier series. And if it's non-zero, that's a good already sign that this term exists. And if it has values that are, let's say, far from zero, that means it's been tunable. So all components here are very well tunable, but in real situations, especially with larger circuits, that's not true. And it's very hard to find circuits that actually where you are actually being able to train well all the terms in the truncated Fourier series. Talking about the combination with classical neural networks, as we discussed, give us different types of functions, different types of mathematical functions. Why not to unite those, right? So to give us a capability to make a function f, which is a summation with weights of a quantum output and classical output. In this case, we let the neural network decide which model works better for this data set, or a combination. So in case quantum is not needed, the quantum weights will be zero. So hopefully neural network can realize this, or the classical will be neglected, or they will be used with some combinations. We did some tests for several small data sets, and by combining quantum and classical, and we specifically liked to look at the data sets we more or less understand that the power of combination should be visible. So we took, as you see on the picture, 2D small data sets where harmonic functions are being combined with noise. So we know quantum can do well harmonic functions, classical can do well, let's say, more abrupt, noisy fitting, because they can overfit much better than the quantum. And we wanted to fit this ground truth. And that's what we see. The variational quantum circuit alone fits well the harmonic part. Multi-layered perceptron, the classical part, really loses this. It was too small to fit the harmonic part, and it really did badly on its own. But if you combine both, the combination of both really outperformed any single architecture. We did further tests. We look at how two quantum work together, how two classical work. In any situation, combining quantum and classical was the best we can look in these types of the data sets. So this, and also in addition to mention why we would prefer to combine, not only in parallel, but we also want our classical neural networks to help us to understand how to load data in the best possible way to a quantum system, how to normalize it probably better for this particular data set. And we want classical system to let us know how to post-process the measurement data. So the combination of quantum and classical really should come into place no matter which hardware capabilities we are going to have. That's always beneficial will always be beneficial to combine quantum and classical. And that's how we see it. Our hybrid quantum neural net is some sort of a graph where some layers are quantum, some are classical. We combine them in some way and get architectures that solve practical problems. Let me talk about the practical problems. To start with a toy data set, we talked about harmonic functions, and again, there could be constructed an artificial test to understand that quantum indeed have an advantage in fitting harmonic functions. The data set is simple. It's from scikit-learn two circles, one interior, one exterior, and there is a noise level, I think around maybe 10-20% of points that are intended to be in the inner circle end up in the outer circle because there's a distribution. And we would like to train our model with small number of points, like shown in this middle part, and test on a large set. As you can see from the middle part, the challenge here is you don't anymore from this sample see the inner and outer circles. And that's exactly the challenge for classical neural networks, because in this situation of small amount of data points, they would tend to overfit, and that's what we tried to achieve. Find a setting where classical overfit just because there's not enough training data, which is, by the way, a very frequent situation, especially in medical applications. And that's exactly what we found. So classical really tend to overfit. When we had more than 50 data points, no problem. Classical was doing quite well, although still worse than quantum. But when we went below 50 points on this small data set, classical multi-layer perceptron really collapsed from, let's say, having 96% accuracy to down to 86 or so % accuracy. That's because it really, yes, that's just overfitting. Quantum didn't have this problem. One more, a bit more complex data set I would like to share with you is predicting the photovoltaic power output. That's a problem we worked with our energy partner, where we wanted to predict how much power would be generated by a solar panel based on the previous history and current solar irradiance, current module, and ambient temperatures. The reason we also want to look at this type of a problem, of forecasting problem, is because we also expect it's related to some harmonic functions. The previous problem with two circles was clearly we tried to find a circle. It was easily found with quantum. Now we want to be a bit more intricate and find how many frequencies do we need to fit the function. How to tweak the amplitudes of our truncated Fourier terms, and we think quantum might have a bit of an edge over classical in this type of a task, although it's much more harder to demonstrate. What we found is when we replaced some classical layers with quantum, we managed to get an improvement in terms of accuracy. We tested different solutions. We looked at multi-layer perceptron, we looked at LSTMs. We compared all of them together, and no matter where we added quantum layer instead of a classical, we observed performance improvement in this task. And you can see on the plot, we also tried to change the dataset size, increased it in a test to see maybe classical would catch up with quantum, but it didn't happen. So no matter which training dataset size we chose, the loss function was lower for quantum analogs. Similarly, we looked at pictures. Pictures are another example where quantum is well applicable due to specific quantum convolutional neural network layers that are quite efficient. We looked at MNIST, standard medical NIST, CFAR datasets. What we observed is that the accuracy, of course, of classical is nearly perfect. We cannot improve over there. But what we found is the possibility that quantum can have a much lower number of parameters, much lower number of weights in comparison to classical, and achieve same performance. And that's what we observed. The accuracy was the same, but the number of weights was significantly lower for the quantum. One more example I want to share is for simulating physical processes. There are special types of neural networks called physics-informed neural networks, where the loss function is being computed based on physics laws. For instance, in this case, Navier-Stokes equation, where we simulate fluid dynamics. And this we did for our chemistry work. We observed that replacing some classical layers with quantum can give us a bit of an advantage in the loss function when we want to estimate what would be the pressure velocity in the geometry of the user's choice. Now, to conclude my presentation, I would like to say a few words about how one would engineer a hybrid quantum neural network. So it's clear that we can move from theory to practice and demonstrate some advantages of hybrid quantum neural nets, but how to engineer those solutions, how hard is it? So what we came up with is a scheme where we divide our process in several steps. We first work with data and pre-processing of this data, understand how to prepare it well to solve the task. When we build the architecture of a quantum neural network layer and hybridize it with classical to build a HQNN hybrid quantum neural network. And this way, capabilities we put inside our Python library called TQNet. Once it's built, it's being optimized using the input from architecture analysis techniques, like one I showed you that analyzes truncated Fourier series terms, but there are more that look at quantum Fisher information metrics, looks at gradients, looks at different expressivity metrics, and it gives feedback to the architecture builder to build a better circuit. Once it's complete, we define what are our hyperparameters, we define what are the learning parameters, execute, and find the best hyperparameters, and once this is complete, do model performance analysis. And using this 5-step approach, we were having quite a good success in solving industrial tasks at scale. I must mention that all the training that we do are still on the classical HPC compute. However, once we train, we do inference on quantum computers to get more understanding whether we can match the performance that we got on a quantum computer, or if noise affects our model in some fundamental way, this is that's why it's still important. But in the future, we see there's a possibility that once there are better qubits, more of them, it should be possible to get some exciting new algorithms in the regime of around 30, 40 qubits. And that's what we are very much looking for. With this, I would thank you for your attention and would be happy to answer some of your questions. So I don't see
Hello?
any.
Like this,
Hello?
Can you hear me now?
Yes.
Okay, perfect. You showed some comparison of different results with the energy grid, where the system size was up to like 10 to the power of 3. What techniques do you use to map this onto qubits, which are, as of now, pretty limited in size?
Could you please, what was 10 to the minus 3?
10 to 3. Like when you went through the, if I saw correctly, the energy systems and the convolutional network, there was a couple thousand variables, but you don't have a couple thousand qubits.
Yes, so a couple of thousand variables in principle can be loaded to a logarithmic number of qubits. So having, you know, like 15 qubits is more than enough to process a couple of thousands of input variables.
All right, thank you.
Maybe a second question. I have just a very quick question. You give us some ansatz, right, which depend of parameter, your quantum circuits, that is correct? Well, you use a rotation on Y and rotation on X, that is correct? Do you have any justification for this kind of ansatz, or is it just of a good idea that I've been experienced in this problem?
It's a good question. So, of course, we can conclude theoretically that some ansatzes don't make sense. For instance, if you initiate qubits in a zero state, then you do rotations around that brings you nothing, right? So that doesn't work. But for all other ansatzes, it's in general hard to understand just by looking at the ansatz if it's a good one or not, especially for different data sets. That's why you would use this analysis techniques. One of them I showed you for this violin plot, where you, by sampling a quantum circuit, would understand which terms are being activated and how much we can tweak those Fourier terms. But in general, you try to use as many indicators as possible to understand if ansatz is good or not. And what we found out that, for instance, this so-called depth-infused neural network layer shows to be quite good in a data set. So that's our, let's say, first choice when we go to solve an industrial task. But we still double check and we still choose which, what's the depth, what's the width of a circuit based on the feedback from this analysis metrics.
Okay, thank you. Last question, maybe? Yes.
Thank you for the presentation. I had a question regarding slide 13, where there is a 21% improvement over classical method. If possible, could we have more details on the experiment setting and what were we for which task we were minimizing that loss function.
How do we minimize the loss function? So if we use, in the classical simulation, we have more flexibility in the techniques that are being used. In the quantum system, there are so-called parameter shift rules, but there are in principle more being in development. As we train on classical system, we use classical backpropagation techniques with which are also standard available as standard in PyTorch.
I think I didn't express myself correctly. What I meant is over which experiment we had a 20% improvement using a quantum algorithm. That was my question in slide 13.
13, let me see.
Yeah.
Over which experiments?
Yeah. What is the experiment? In which setup we had a 21% improvement?
I showed you briefly this slide. This was a physics-informed neural network where we simulated fluid dynamics. Share it back. And the goal was to put different fluids in the left and the right-hand side arm and observe what would be the mixing result of those shape. So this is a Y-shaped mixer, certain geometry, certain diameters of this input arms. And to understand the result of the mixing, we want to compute pressure and velocity in each point of this geometry. Classically solved by physics-informed neural network. Quantum is solved by replacing classical layer with a quantum in a particular place.
Okay, thank you.
And we have a published work to look a bit more at this use case.
Okay, thank you very much for your presentation, Alexey. Thank you very much. And
it's a pleasure.
We hope to see you in next event, maybe, or in conference. So thank you. For us, it's time to have a coffee break of 30 minutes.